In this video, I'll demonstrate how to obtain static characteristics of field effect transistors, namely JFET and MOSFET, using OrCAD's PSPICE simulation tool. Mainly, FETs are divided into two types, JFET and MOSFET. JFET stands for Junction Field Effect Transistor. Once again, there are two types, N-channel JFET and P-channel JFET, and the corresponding circuit symbols are as shown in this diagram. This is N-channel JFET, this is P-channel JFET. One more type of field effect transistor is MOSFET, which stands for metal oxide semiconductor field effect transistors. Once again, there are two types of MOSFETs. One is depletion mode MOSFET and another one is enhancement mode MOSFET. In both the types of MOSFETs, once again we have N-channel MOSFET and P-channel MOSFET respectively. And these are the circuit symbols for different types of MOSFETs. In this video, I'll demonstrate how to obtain characteristics of junction field effect transistors, both N-channel and P-channel, and NMOS and PMOS of enhancement only MOSFET types. First, let us see how N-channel JFET characteristics looks like. You can characterize N-channel JFET using two types of characteristics. One is drain characteristics, another one is transfer characteristics. To obtain both the characteristics, this is the circuit that we have to build. We have N-channel JFET here, and we shall apply gate to source voltage and drain to source voltage. Two voltage sources are required. To obtain drain characteristics, what we shall do is we'll fix up gate to source voltage VGS constant, and we shall vary VDS starting from 0 to some positive value of the voltage, and we have assumed this as the direction of the current. As VDS increases, keeping VGS constant, if I increase VDS continuously, ID will also increase to certain extent, and after a point ID becomes constant. Even if you increase VDS, ID will not increase. This is how drain characteristics looks like, and we shall apply positive voltage to VDS and negative voltage to VGS. If VGS is 0, the device is on. To turn off the device, we shall apply negative VGS. However, in the circuit, positive is represented this side, but when we specify the voltage, we will specify negative voltage. So drain characteristic relates voltage across the device, that is VDS, and current flowing through the device for different values of VGS. And to obtain transfer characteristics, what we need to do is we'll fix up VDS. We will not change VDS. We'll provide some positive value to VDS, and we will change VGS. And for N-channel JFET, VGS should be negative, so that's why I have kept a hint here. VDS is positive, VGS should be negative. So we shall increase the negative voltage. So that is shown in this graph. From 0 to -5, VGS is increased, negative voltage is increased, and as VGS becomes more and more negative, the current will drop. This is the transfer characteristic. Let us see how to obtain these characteristics using OrCAD PSPICE simulation tool. Before performing simulation, it is recommended to create a separate project, a separate folder in which you will create the project. So I have created a folder called as FET characteristic. Inside this, I will create one more folder for obtaining N-channel JFET characteristics. So I'll name the folder as N-channel JFET characteristics. I will create the project inside this folder. Please note the path before you create the project. This is the path where I have created the folder. So I will open Capture CIS Lite. I have already installed this, so I'm getting this option. Once OrCAD Capture CIS Lite is open, I don't want start page, I'll just close it. I'll go to File, New, and click on Project. I'll give a name to the project. This is N-channel JFET characteristic. So I'll give N JFET characteristic. Please browse and choose the folder that you created for this purpose. So I created it somewhere here. I will browse to that particular folder, N channel JFET characteristic, and I'll select that folder. Then I'll click on OK. Here I'll select create a blank project. Click on OK. If you move to the bottom right portion, you can fill up the title, document number and revision number. So the title is N channel JFET characteristics. Document number I'll enter as 1. Revision code I'll enter as 0.0A. This depends on the standards that you follow. This is the standard what I follow. So once the title block is complete, I can start building the circuit. The circuit is very simple. So I need one N channel JFET. So I'll choose 2N5457. This is the N channel JFET. So I'll go to place part. Here I'll have to add a library called as JFET. So I'll click on add library and I'll search for a library called as JFET. So here I have jfet.olb. Add this and you will find the part as J2N5457. J is the standard prefix that is added in the PSPICE environment for JFET tools. So the actual device is 2N5457. So just place it somewhere here. Apart from this, I need 2 voltage sources. So I can get the voltage sources from the source library. So I'll select source library and I'll browse for VDC. So this is VDC. I need 2 voltage sources, one for VDS, one for VGS. Apart from that, I also need a reference point, ground. So I'll click on place ground and I'll select 0 bar capsim. Click on OK and place it. Then using place wire option, connect all the components together as per the circuit diagram. I'll name this voltage source as VDS. So double click on this part reference and type VDS, and this V2 I'll name it as VGS. So double click on the part reference and type VGS. Now don't worry about the voltage values. What should be given? Let it be 0 volt DC. Please save the design. We shall perform a DC sweep analysis. So to perform DC sweep analysis, we'll have to create the simulation profile. For that, I'll go to PSPICE from the menu bar and click on new simulation profile. I'll give name to the simulation profile. I'll perform I'll extract drain characteristics first. So I'll give drain characteristic as the simulation profile name. Click on create. Simulation setting window opens. Select the type of analysis as DC sweep. In DC sweep, what happens, the PSPICE simulation tool will automatically change the voltage or the current source what we select automatically, and it will note down the output variables for each of the values of the source what we have selected. So in DC in drain characteristic, please look at the sample waveform. X-axis is VDS, drain to source voltage, that is being varied, and y-axis is drain current. So whatever is there in the x-axis, that is your primary sweep variable. So VDS is the primary sweep variable. So in the primary sweep, select voltage source. The primary sweep variable is VDS. So enter that. Start value you can give 0. End value I'll sweep it up to 25 volt. instep of 0.1 volt. This you can give any value, you can even give 0.01, your graph will be much smoother. And what should be the end value? There is nothing called as a predefined standard. You have to experiment. After all, you are obtaining the characteristics, you do not know what is when the device will break down. That's the reason why you are doing this experiment. So I'll give 25 volt and keep the sweep type as linear. So PSPICE will automatically change the drain to source voltage from 0 volt up to 25 volt in steps of 0.1 volt each time, and it will note down the different circuit parameters for each of the values of VDS. And we have to repeat this experiment for different values of VGS. So how do we do that? So I'll enable parametric sweep. So select parametric sweep, primary sweep is over. Now primary sweep must be repeated for different values of VGS, so that I will enter in parametric sweep. So that can be seen here. So primary sweep is this VDS, and this is repeated for different values of VGS. VGS is 0, VGS is -1, -2, -3. So that goes in parametric sweep. So parametric sweep source is once again voltage source, it is VGS. It is case sensitive, please type correct reference designator. Specify different values. So I'll click on value list, I'll select value list and I'll enter it manually: 0, -1, -2, -3. You can go on entering different values also. So this is very simplest case. So click on apply, click on OK. Then you can run the simulation. Yes, it is done. And see, the simulation is performed for different values of VGS: 0, -1, -2, -3. If you want to plot all the graphs, you will have to select everything and click on OK. Then only all the graphs will be available. Please see, x-axis variable is already voltage VDS, 0 to 25 volt. Now what is y-axis? That is the current flowing through the device, drain current. So I will add drain current. So you can right click, add trace and select ID of J1. Select this one, click on OK. Or you can go back to the design without closing the simulation output window, and you can get current marker. Click on this and pin it to the drain terminal. Both are the same. So these are the different curves that I have got. Now which curve is for what value of VGS? How to identify? That is the problem. That is very simple. You can select a particular curve, right click and click on trace information. You will get to know what is the value. So this is for VGS is equal to 0. So this green curve is for VGS is equal to 0. So I keep forgetting that. So what I can do is click on this. You can add a label to that so that you don't have to see the trace information every time. So I'll add text label and I'll say VGS is equal to 0 volt. So click on this and just put it on top of this. Similarly, what is this curve for? So I'll just right click on this, I'll click on trace information. This is for VGS is equal to -1 volt. So I will add text to it. VGS is equal to -1 volt. Click on that and just place it somewhere near this. Similarly, you can do for other things as well. So this is the drain characteristics of the N channel JFET, and you should also observe the pinch off voltage. So this is where the saturation occurs after this VDS value. Switch on the cursor and check. So this saturation is occurring at VDS is equal to 1.3508 volt, and left to this region is the ohmic region or the linear region. right side of this is the saturation region. This is how you identify. Of course, it will change for different values of VGS. If you want to get a print of this, you can go to File and you can even print the graphs. If you do not have a printer, you can always preview this, print preview. This is how it appears. If you are not happy with the color, this is green color in the white background and this is yellow color in the white background. If you are not happy with the color, you can even change the color. So I'll just go to trace and I'll switch off, I'll freeze the cursor. I'll select the green color. I do not like the color of this trace. You can right click on this and you can click on trace property, and even you can change the color of the trace and also the width. If you want it to be slightly thicker, you can select the thickness, width, click on OK. Now if you can go to print preview, this appears very thick and it is very much visible. That depends on your requirement. You can change the different thickness. You can select, you can print here and you can save it as a PDF. If you do not have a printer, then you can save it. You can print it to a PDF file. So select Microsoft Print to PDF, click on OK and select somewhere else and say drain characteristic. Click on OK. I have selected desktop. So a file is created on my desktop. So I'll just show it to you, drain characteristics.pdf, and this is how I get. Let us simulate transfer characteristic for this. I'll create one more profile. So you can go to PSPICE, click on new simulation profile. This time I'll say transfer characteristic. Click on create. For transfer characteristic, what we'll do is we'll fix up VDS, we'll change VGS and note down what is the current flow, drain current flow. So input is this side and y-axis variable is ID, that is at the output loop. That's why it's called as transfer characteristic. So please see here the sample graph. VGS is negative, it is in negative voltage, so we have to apply negative VGS, and VGS is the primary sweep variable, and we shall do it for some value of VDS. So analysis type must be DC sweep, primary sweep voltage source must be VGS, and it's a negative voltage, so I'll give the lowest value first, -5 to 0. You cannot give 0 to -5 because start value has to be always lesser than end value. I'll give the increment as 0.1. You can give 0.01 as well. If you want to repeat this for different values of VDS, you can select parametric sweep also. I'll select parametric sweep and VDS is the secondary variable, and I'll give a list that is better. I'll give 5 volt and 15 volt for two different values of VDS. Again, there is no rule that you'll have to select 5 and 15. You can select any two values. So click on OK. Now please select transfer characteristic simulation profile and then run it. Please see here x-axis is VGS. Now you can add drain current, add ID of J1. So this is how it appears. There is a slight difference in the curve for different values of VDS. You can right click on a particular curve and you can click on trace information to know for which value of VDS that curve has come. If you want to add label, you can add the label and you can take a print of this characteristic. Now let us see. For your reference, I have added this small hint. For P-channel JFET, VDS must be negative and gate voltage VGS, gate to source voltage, must be positive. So VDS must be negative, VGS must be positive. To obtain the drain characteristic, primary sweep variable is VDS and secondary variable is VGS, which must be positive. And for transfer characteristic, VGS must be positive and for different values of VDS we can obtain, and VDS must be negative. So I have already created a project for that. To save the time, I'll just open that. I'll close this particular project. I'll just close it. Right click, close everything. I'll open the project directly. I have created already a project. I'll open that project file. And this is the circuit. This is the circuit. We have not changed the directions. We have assumed this as the direction. So let me show you the simulation profiles. I have created two simulation profile. I'll show you the drain characteristic simulation profile. I'll just select this and I'll click on edit simulation profile because I have already entered the values. Primary sweep variable is VDS for drain characteristic, and VDS must be negative. So I have selected from -20 to 0 in steps of 0.1, and I want it for different values of VGS. So I have selected parametric sweep also. In the parametric sweep I have given variable as VGS, and for different values of VGS, which is positive 0, 1, 2, 3. So I'll run this. So I'll select OK. We have got VDS as the x-axis variable. Now I'll select the current marker and I'll pin it to the drain. So this is the curve that I've got. But if you look at the data sheet, most of the data sheets, the curve appears like this. But if you carefully observe the x-axis is negative. 0 is towards the left and negative is going towards the right. And also the current, 0 is towards the bottom, current is indicated in negative, increasing magnitude. However, there is a difference in the PSPICE. Please observe, 0 is towards the right and -20 is towards the left, and also 0 is at the top y-axis. This is -5 milliampere. We can always change it to match to that of the data sheet, or you can leave it as it is. That depends on how you want to analyze. If you want to change the direction, so what I'll do is I'll double click on this x-axis, somewhere on this x-axis. So this axis setting window opens. I'll select x-axis. I'll select user defined. Here it says -20 to 0. I'll interchange 0 to -20 volt. And similarly, I'll go to y-axis. It says auto range. I'll change it to user defined. It says -5 milliampere to 0 ampere. So I'll change this to 0 ampere to -5 milliampere. Click on OK, and your graphs will match to that of the graphs shown in the data sheet, most of the data sheets. So this is the drain characteristic. I'll run the transfer characteristic. First I'll show you the simulation profile of the transfer. I'll edit the simulation profile. I have already entered the value. Once again, it's a DC sweep. Primary sweep variable is VGS, and VGS is positive 0 to 5 volt in steps of 0.1, and for different values of VDS, VDS is negative. I have selected -5 and -10 in the value list. You can select any two different voltages. So I'll click on OK, and then I'll run. Because I've already placed the current marker here, I'll get the graphs directly, and this is how the graph appears. If you want to match it with that of the datasheet graph, you can always change the axis. Please see here, VGS is positive, 0 towards left. Drain current 0 is in the bottom, increasing negative value, negative magnitude. So I'll change only the y-axis. X-axis is proper, only y-axis I'll have to change. Double click on y-axis, select user defined, say 0 towards left and -5 milliampere towards top. Click on OK, and it will match to that of the data sheet. To know which curve is for what value of VDS, you have to just right click on a particular curve and click on trace information, and you will get to know the value of VDS corresponding to that. So this green curve is for VDS is equal to -5 volt. Similarly, you can right click on red curve and click on trace information, This is for VDS is equal to minus 10 volt. You can add the label and you can take the print and store it. This is the characteristic of P-channel JFET. Now let us see how to obtain characteristics for NMOS. NMOSFET will also have two characteristics, drain characteristics and transfer characteristics. Here VDS should be positive. Please observe the circuit symbol. This is enhancement type, so the channel is not formed. So the channel is indicated as broken. We'll have to apply gate to source voltage to form the channel. So VDS must be positive. I have given the hint here, and gate to source voltage must be positive as well. If you increase gate to source voltage, the current will also increase. And x-axis is VDS positive, y-axis is drain current, and VGS is also positive for drain characteristics. For transfer characteristics, primary variable is VGS, that is positive, and for different values of VDS you can obtain the transfer characteristic curve. I have already created the project. I'll just open that and I'll show it to you. I'll close the existing one. I'll open the MOSFET, N-channel MOSFET. This is the circuit diagram. Once again, I have not changed the direction of current or the polarities of the voltage sources. So let me show you the simulation profile of the drain characteristics. Once again, the analysis is DC sweep analysis. Primary sweep is VDS 0 to 20 or 25 volt in steps of 0.1 volt. For different values of VGS, so I have selected parametric sweep. VGS is the sweep variable and I want curves for VGS is equal to 0, 1, 2, 3 volt respectively. So click on apply, click on OK, run the simulation. I have already added current marker here. So click on OK, and this is the characteristic what you get. You can right click on the graph, particular curve, you can get the trace information. If you want to add label, you can add the label and take a printout of it. So let us run the transfer characteristics. For transfer characteristics, primary sweep variable is VGS, so that is swept from 0 to 5 volt in steps of 0.1. For different values of VDS, so that is the parametric sweep variable, and I want to run for VDS is equal to 5 and VDS is equal to 10. So let me run the simulation. Please select transfer characteristic when you are running this particular simulation. So I'll click on OK. Oh, current marker is not added. I'll just add it. So this is how the curve looks like, and it is matching to that of the characteristic curve what is shown in the data sheet, and you can find out where is the threshold voltage. So last type of the MOSFET is PMOSFET. Please note the circuit symbol, the arrow is going outwards. Once again, this is enhancement type MOSFET. Channel is not there. To create a channel, we'll have to apply negative voltage. And this is how the drain characteristics look like. VDS must be negative. This is negative voltage. VDS must be negative. And VGS is also negative. Both are negative in this case. So let me run the simulation and show it to you. I'll close the existing project. I'll open the project. PMOSFET characteristics. So I'll show you the drain characteristics. Primary sweep variable is VDS 0 to minus 20, and for different values of VGS, which is also negative. These are 4 different negative voltage values. So I'll run the simulation. This is the graph that I've obtained, but it is not matching with that of the graph shown in the data sheet. So you'll have to just reverse the axis. it is from -20 to 0. You'll have to just change this axis from 0 to -20, and y-axis from -10 milliamp to 0 to -10 milliamp. Click on OK, and you will get a graph that matches with that of the data sheet. Now let me run the transfer characteristic, and these are the settings. Primary sweep variable is VGS, that is also negative, -5 to 0. Always start value must be lesser than end value. And for different values of VDS, -5 and -10 both are negative voltages. Click on OK. I'll run this simulation. And this is how the graph looks like. Again, to match this, I'll change the axis variables direction. So double click on the x-axis, and in the current, interchange 0 and -150 milliampere. So this completes the demo on how to obtain static characteristics of different types of field effect transistors. Thank you.